Okay, let's talk about two LCA question. Lowest common ancestor. The first one is a little bit easier one. It's the LCA of binary search tree. So there's the BST's properties that we can utilize. The second one is a little bit more general. It's the lowest common ancestor of a binary tree. So we lose that BST property. So this has to be able to deal with that. So let's talk about this one first. The definition for lowest common ancestor, I guess, if you draw the tree with the root node on the top and the leaf nodes on the bottom this way, then the higher it is, the higher up the node, it's considered higher. The lower the node is in terms of the levels in there, it's lower. And the LCA between two nodes, P and Q, is the lowest node in the tree that has both P and Q to be its descendants. So a quick note here is that a node can be its own descendant. It's quite important that this property here. So let's look at one of the example. If we look at P, Q to be 3 and 5, the LCA is 4, which has a value that's being sandwiched in between. If we look at maybe like the 3 and 0, the LCA, we can just obtain that by visually tracing the edges back to until the first place the two passes reached converged. The LCA between 0 and 3 is 2, which has a value that's being sandwiched in between. And let's look at one last example, 2 and 4 or 2 and 3. Since that 3, 4, 5, these three nodes are all descendants to 2, and the LCA between 2 and any one of those three is going to be the node 2, because 2 is its own descendants and the other one is also its descendants. So the values will be like 2 less than equal to 2 less than 4. So the sandwich of the values for the two nodes and the LCA it's inclusive. So that's pretty much the observation when we run through some examples. Why is that? Why is the LCA's value must be sandwiched in between? Because all the left descendants for any given node has a value that's smaller than the node's value. All the nodes that's towards the right descendant of a node has a value that's larger than it. So if you want to find the common ancestor of two nodes, that LCA node's value has to be in between. Otherwise, there is no way that it's going to be a common ancestor. So let's say that just quickly show that by contradiction. Let's say that we are looking for two nodes 0 and 3, and we're considering node 6 to be the LCA. Since that both 3 and 0 has a value smaller than 6, they are to the left subtree of this node. So we can always just go left to find another common ancestor that's lower compared to this node here. That's the same situation when you have two nodes that all have two target nodes all have a larger value than the candidate that we are looking for. So basically the relationship between these two nodes, target nodes value, and the nodes we are considering, is going to tell us which direction we go to keep searching. And because another observation to find is that once we find a node that we enter this binary search tree through the root, through that direction, based on that comparison as direction, when we find a node that's sandwiched in between, it has to be the node, because at that given time, since that the value is sandwiched in between, and the two nodes are to two different sides of the node. So if we go either way, we will lose the other one as the descendants. So that's just a really quick, sketchy kind of proof about why this works. And in terms of time and space analysis, we enter the tree using from the root. We're gonna at most do one pass to get to the bottom leaves. There's no going back and anything, so we're gonna end up with the time that's proportional to the height, about roughly the height of the tree, and that's the same about space as well. So we're gonna code up a recursive version because it's relatively easier to code. You can convert it to iterative with a little bit more work, and not so much in this question, but for the next one, the iterative version is gonna be difficult. So let's code. So if we don't have any root, we just return. That's handling edge cases. Otherwise, we still want to return the root. And we're gonna recursively do the search for a new location from a new candidate, and to determine whether we go left and go right to update the candidates. It's depend on the nodes value to target nodes value, its relationship with this candidate nodes value. So it's let's say that we have this case here would be that all the two target nodes are to our left hand side. We have to go left. The other extreme, the other alternative is that all these two nodes have values that's larger than us, so it's we have to go to the right to find a lower common ancestor. So this is pretty much the code. It's relatively simple, and let's look at the slightly more difficult one, which is the LCA of two in a binary tree. So the only thing that we can do with this node is that checking the reference, whether they are the same reference, the variable, whether the variables are referencing to the same node object. The checking the nodes value wouldn't give us any kind of maybe only the equal sign, equality check. We're not going to be able to get any kind of directions by comparing those values as compared to this easier version. So then we start to think about how at each individual nodes level are we going to be able to make a decision about the LCA's question, right? So let's say that we are at node 5 and we are looking for node 6 and node 4. Just to think that I am node 5, what kind of information I would need from my descendants from both sides for me to make a rational decision what node could potentially be the LCA. That's not what I would know is what I would want to know is that can I find a target node from left? Can I find a target node from right? If both of them telling me that yes, there is a P, there is a one node here and the other node in the right, then if I'm the first one to discover that, I must be the LCA. So that's one case. The other case is that if one side cannot find the target, the other one can find at least the one, then even though I'm not an LCA, but I can tell my upstream that through me you can find at least one of the node there. So that could be also important for me to return. If through me, if both of my children found nothing, then I just return myself, right? So that's pretty much what the node needs, and what the nodes need to, what's the node takes in, and what's node's responsibility to its upstream. So it's going to be recursive, like we call this function recursively for both my left and right, and somehow aggregate the information I got and propagate that back to my upstream. That's pretty much the recursive kind of a solution. I guess that one of the edge cases. We're gonna start code and talk about the edge cases later on. So because it's we have to reach the end to determine whether through one of the paths can find one of the target node. It's kind of a DFS, so we're gonna call this helper function DFS. Yeah, again, for me to make a decision, I need both information from my left and right by calling the same function recursively on both sides. And if both of my sides return a node, that they found, then I must be the first LCA nodes. I'm just telling the, I'm just going to tell my upstream, I'm the LCA. So with this, when I go further down in there, I find that P or Q, I just propagate that back to my upstrings. So when both L and R returns something, some non stuff, that's meaning that from both sides I can find one of the from both sides I can find the targets. So I myself is going to be the LCA. Otherwise, I would just test do I have something? So that's pretty much the logic. As a tree myself, as a whole, I'm just gonna call this on root. So that's pretty much the code. I guess one thing to mention is that the property here, a node can be its own descendants. So if let's say that the node is 5, if you ask a left, it's none. If you ask a right, it will return. Let's say that one more concrete example. Let's say P is 5, Q is 4, and we reached this node 5 here. The left branch is telling me nothing, it's null, and so L is null, none, and right returns a node 4. So, but I have to return myself. If you're just looking at this code here, if right, I should return right. That doesn't seem right, but when you see the first line here, it's actually handling that. So if myself is one of the node, I'm just going to report to my upstream, I'm one of the node that you're looking for. But if the other branch returns nothing, it's the other branch in parallel to me returns nothing to my upstream. Then I'm the only one that's reporting the root to the root. I have something here. Since that I think the question says that P and Q are different and both exist. Since that I'm the only one reporting I existed, I'm just going to be the LCA, because the other node, since it's not in the other branch, it has to be in a descendant to me, and I'm just reporting myself, but I'm pretty sure that the other node is in my branch. So that also, this line also handles. It's the base case, it's the base case reporting for every node, but it also handles that this condition here. So it's a quite a interesting line there. So I guess this should work. Just back propagating the information about the possible LCAs all the way back to the root, and from root you return that candidate. I guess one thing you can improve upon this recursive version is that using some kind of counter to count the number of nodes you find. And once that hits 2, and you have a node that first declare that I am truly the first LCA that you detected in this search, then you can terminate this BDF search first, earlier. Let's say that just looking at this example, we're looking for LCA between 6 and 2. We go left. We first go left, and somewhere in there we have already figured out there is no way, no need that we run any kind of DFS recursively on the right. So that could be a potential improvement on top of this. Yeah, but I'm not gonna do that today. So let's see if this code works. Yeah, it's working. It's mediocre. Just one final note here. This code is going to be, since it's like a DFS, it's the queue. No, the stack is going to be the proportional to the length of the tree, and in the worst case, it can span the tree. If the tree is degraded, it can be linear. And time is linear as well. It's guaranteed that we have to visit every node, so it's linear in time and space for this approach. Beyond that is iterative version of this question is actually really difficult, quite difficult. Not super, but they're really difficult, and because mimicking this stack call is it's a little bit tedious, and you have to use some extra stuff to keep track of the states, so it's quite challenging. So I leave it to you to try it out, I guess. So bye for now.